In this A3 tutorial, I'm going to introduce three-phase systems, but I'm not going to do it like a lot of people do it, with a lot of mathematics, or by focusing on balanced systems, because focusing on a balanced system gives a very misleading idea of what's going on. What I'm going to do is I'm going to take a single-phase system and build it up into a three-phase system, and from that, hopefully you'll get an understanding, a visual, a very graphical understanding, done with a simple calculation and some simple, straightforward numerical solution to show you what's going on in a three-phase unbalanced system. Now, with an ideal neutral. This method assumes the neutral wire is an ideal wire. So to start off with, let's look at our simple single-phase system. We have a supply over here, and we'll call it 230 volts, which is feeding a load here. And we'll call our load, we'll just call it 5 ohms. Now, the voltage, the AC waveform here is a sine wave. And as I've just said, it's got an RMS voltage through here of 230 volts, RMS. And that means the peak voltage is 325 volts. Bearing in mind that the relationship between those two is root 2. Now, on the subject of all of these roots, in a balanced system, you'll often see a root 3 be bandied about. This is an unbalanced system, so we do not go near root 3s, okay? If you want to understand three-phase systems, we need to completely forget about this root 3 business. The whole idea around root 3s is it's a numerical fact that applies for balanced systems, but it's a gross simplification of what's going on. And as you progress through your university studies, you'll find that all the stuff you learned is a simplification of something that gets harder and more complex. The root 3 is a simplification of what I'm going to go through today when everything is balanced. But we're looking at unbalanced systems. So, coming back to our system here, we know that the current flowing through here is the voltage over our impedance, which is 230 divided by 5, which is a current of 46 amps. If we were to plot that on this time domain waveform here, we would see a waveform that comes through somewhere around about this dotted line with an IRMS of 46 amps. This is fairly straightforward. What we can also show is we can show it in a vector diagram where this is our 0-degree reference point, and we can show our voltage waveform here, which starts at our 0 degrees here, and so everything is referenced to this. Our current waveform as well is exactly the same. It starts at that exact same point. Our reference point is 0, so we can see that if we were to plot our currents on here, that would be there. I equals 46. Now, a three-phase system has 3 voltage sources driving into 3 lines into 3 separate loads. These voltage sources nominally are all the same magnitude, but they're 120 degrees apart. Each one of them is 120 degrees different from the other one. So if we look at that in the time domain here, we know that one cycle here is 360 degrees, and half of that is 180. So that's 120 degrees, that's 120 degrees, and that's 120 degrees. And if we were to look at all 3 of our voltage sources, we would see a waveform that looks something like this. what we can do now is we can start labeling some of these, and we'll call this one here our reference. We'll call that A. The one that lags by 120 degrees we'll call B, and the one that lags that we'll call C. So we can come back to our notation here, and we'll call this VA for our supply voltage number A. We'll call this our impedance A, and this is our current A. This is our reference point, so we can add on to a few things onto here. It's got a reference to 0, it's in phase. This one here has got an angle of 0. So we now have our single phase A in our schematic. Here it is in our time domain, and here it is in our vector domain. What we need to do now is take our second and our third phases and populate our schematic and our phasor diagram with this information. And the way that it's normally drawn is something like this. With our three phases coming out like this. This is the reason this system is called a star system. Three-phase, our neutral wire, everything's configured in a star. The reason it's drawn as a star or shown in a star is in part to show our 120 degrees here, and 120 here, and 120 here. It would be equally valid, and you'll often sometimes see this drawn as something like this, where you've got your three supplies coming like this, and they come into our three loads. That schematic there is equally valid, but you'll often see this one here. What you'll also often see is you'll see a couple of these lines crossed over, because people like to draw this one as VA, VB, and VC, and they like to go ZA, ZB, ZC. The way that I've drawn it here is just slightly more simple, but a little bit different from what you'll see in some books. Some books show it this way, some books show one of them twisted around with a few lines crossed over. So again, let's go through and take our schematic and label it. So we're going to call this one here VB, and that is 230 degrees, but it is lagging by 120, minus 120. VC is likewise 230, and it lags our reference by 240. We can come back here and we can see that any particular point in time, the peak of this one relative to the peak of this one is 120 degrees. The peak of this one relative to the peak of this one is 240 degrees. Between these two is also 120. So we have 120 degrees of phase shift between any of these waveforms, which is what we show here and what we see here in the time domain. In the vector domain, the phasor domain, depending on which terminology you want to use, we can draw these in as well. Phase B lags by 120. This thing circulates in this way, so to lag, we would come down here. VB, 230 volts minus 120 degrees. And similarly, VC will be up here somewhere, 230 volts minus 240 degrees. The question is now, what are the currents? We've established this current from this supply feeding into this load. We now need to calculate the currents in line C and line B. In order to find those currents, we need to know what these impedances are. And so I'm just going to stick some values in here so we can go through and we can work these to show something out. But as I've said, this is going to be an unbalanced system. We've got a balanced supply. This is all perfectly balanced, all same magnitudes, all the angles are equally apart. But I'm going to mess the system up with some unbalanced loads. And in phase B, I'm going to put in a resistance of 5 ohms, and I'm going to put in an inductance of 15 millihenries. We know that to calculate the impedance, is R plus JXL. We know what the resistance is, there it is, 5 ohms, but we don't know what XL is yet. So we can come over here and we know that XL is 2 pi FL, 2 pi times the frequency times the inductance. As this is a 230 volt system, we're going to assume it's 50 hertz. And so we can calculate our inductive reactance, XL, 2 times pi times 50 times 0.015, 4.71 ohms. So our impedance here is 5 plus J 4.71. Our current, as we've set up here, the same expression, the current through this impedance here is the voltage over this impedance divided by the impedance itself. So the voltage over that impedance is this one here. We can follow along these wires, it's here. 230 volts, an angle of minus 120 over our impedance of this. Now we can't do this calculation because this is in polar form and this is in rectangular form, so we need to convert this to rectangular. We can do that. Polar of 5, 4.71, close bracket, equals, gives us 6.87 at an angle, recall F, of 43 degrees. 6.87, angle 43. To do this, we divide the magnitudes and subtract the angles. 230 divided by 6.87, 33.48 amps, minus 120, minus 43, minus 163. So here we have our current. A magnitude of 33 amps, that's what you'd see if you stuck an ammeter in this circuit, but it's got an angle of 163. You would not see that with your ammeter. And this is something where a lot of guys with a trades background come into it and have a bit of a difficulty with. They know this number, but they don't know this number. They think it's 120 degrees. We've just shown it's not. What this one is it's lagging by 163 degrees. So 0, minus 90, minus 180, that's too far, it's back here somewhere. We know that this is 120. So we'll add another 43 degrees onto that, and here it is out here somewhere. IB, 33.48 at an angle of minus 163. Now, you may have already noticed that the difference between these and these is obviously this angle here. That angle there is 43 degrees. We can now go through and do the exact same process to find out the current flowing in line C. So for line C, what I've decided to do is we'll put in a value of 7 ohms of resistance, ZC, 7 ohms, and we'll put in 600 microfarads. Because this is a capacitive, it's going to be minus. This is in this area where a lot of students make mistakes. They drop some of the signs in doing their calculations. It's very important to keep these signs very clear. That's a C, so that will be a minus. And we can calculate the value of capacitive reactance. 1 over 2 pi FC, 2 times pi times frequency times 600 microfarads gives us an answer of 5.3 ohms. So 7 minus J 5.3. we need to convert that to polar form using the same process we just did up here, and that gives us an answer of 8.78 at an angle of minus 37 degrees. We can therefore calculate the current through here, because we now know the impedance, we've assumed a few values, we know the voltage across here. The voltage across here is that voltage. Which is 230 at an angle of minus 240 divided by our impedance, 8.78, angle of minus 37. (230) divided by 8.78 gives us a magnitude of our current of 26.2 amps, and again that's what you'd see if you stuck an ammeter in the circuit, and it has got an angle of minus 240 minus 37, and that comes out and will give us an angle of minus 203 because of some rounding that I've just done. Okay, and we can again plot this one over here in the phasor diagram. We've got a magnitude of 26 and it's at an angle of minus 203, minus 90, minus 180. Oh, too far, we need to come back. We know that that's minus 240, minus 200. It's going to be up around here somewhere. I see 26.2, an angle of minus 203. And again, this angle here between these two is 37 degrees. The angle between our voltages here and here is 120. And between this one here and this one here is 120. Now, if we were to plot these currents in the time domain, like we did up here, we'd get something quite different from this. We'd get something that looks a little bit like this. We could do that. We can just do a quick sketch. It'll be a rough approximation. Our phase A current is here and it's in phase, so it's going to look a little like this. Okay? Our phase B current is lagging by 163, so we know that that's 90 and that's 60 and 123, so it's going to be lagging by more than our 120 degrees like our voltages. Remember, this zero crossing here to this zero crossing in our voltages here is 120. Well, this one here lags by 160, so it's not going to start here, but rather it starts here. And it'll come through here. Phase C is lagging by 203. So here's 180, 270, so it's going to be here. We can see here, obviously, that that and that to that is not equal to 120. And likewise, this one here is not equal to 120. Our system is unbalanced. If we were to go through and add up all these voltages up here at any particular point in time, because the system's perfectly balanced and there's supply voltages, all of those voltages there, that value plus that value plus that value would equal 0. The sum of our voltages equals 0. With this one here, if we were to do it, say here, the sum of our currents does not equal 0. We can see that here in the time domain, and we could also see it here in the phasor or the vector domain if we were to go through and add these up. This is a fairly rough sketch, but if we take the length of this one and add it to this, we'd end up here, and we take the length of this one and add it to here, and we end up down here somewhere. The vector sum of these is somewhere down here. It is not 0. this is why we need the neutral wire, because this vector sum of all of these currents, we can't have this point here not equal 0. This point here has got to equal 0. This is a fundamental point of first year physics and first year electrical engineering 0. All the currents into this node have got to equal 0. The current from here and here and here, we have seen in the vector diagram, does not equal 0. We've seen it here in the time domain. It doesn't equal 0. The only way we can make this point here equal 0 is by having a current here in the neutral wire. The current here in the neutral wire will make this lot equal 0. So we now need to calculate what is the current in the neutral wire. To do that, we need to add all of these currents up to find out what this point here is going to be, and then the neutral current will be the polar opposite of that. So let's go through and do that. We know that IA is 46 at an angle of 0. IB we calculated to be 33.48 at an angle of minus 163, and IC to be 26.2 at an angle of minus 203. We can't add these values up like this. We need to convert them to rectangular, and we can do that reasonably simply. Rectangular of magnitude of 46 at an angle of 0, and this will come up as 46 plus J0. Here it is, 46 plus J, recall F, 0. No surprises here. This one here, IB, rectangular, 33.48, comma, minus 163. Now this is another area, again, where students often make mistakes, like I said before, is they start dropping these signs out. Bad move. Keep your signs in, otherwise you'll get the wrong answer. Minus 32, recall F, minus J, 9.8. Now we've done a calculation, we've got a number. In an exam, a lot of students who are doing this sort of stuff will just leave it at that. Unwise. We've got a plot over here. We can check our number. Have we made a simple calculation error in this stage? Let's have a look at our plot. It's minus 32 in the real direction and minus 10 in the imaginary direction. So that makes sense. We can see it down here. Minus 30, minus 10. Our sketch is pretty rough, but it's in the ballpark. Our calculation matches our rough sketch. That seems okay. Let's do the second one. Rectangular conversion of 26.2, an angle of minus 203, close bracket, equals minus 24, recall F, an angle, imaginary component of plus 10.2. Again, we can come over here and look at C, minus 24. We said that this was minus 30, and that's kind of in the ballpark. Plus 10. Again, our calculation matches what our plot is, which tells us our calculation is correct. We can therefore go through and add all these up. (46) plus minus 32 plus minus 24 gives us a solution of minus 10. We need to do the imaginary part. 0 plus minus 9.8 plus 10.2. 0.4. We can now look at this over here, and we can say that our vector sum, which we've just done here, does this look close to what we did over here? And yeah, it does. I mean, in my rough sketch, using the length of my pen to do that before, I speculated that it was here. My calculation shows that it's probably closer to back down here a little bit. It's because we roughly agreed this was about 30 odd. So it's probably down this way a little bit, and it says it's a plus 0.4, so it's actually, so strictly speaking, it's probably up here. Okay? My rough sketch was kind of close enough. Our calculation supports our rough sketch. It tells us we're doing okay. So this is our sum of our currents here. To find out what our neutral current is, it's very simple. We need the exact opposite of that, of this one here, the exact opposite. So therefore, our neutral current is the exact opposite of minus 10 is 10. The exact opposite of J.4 minus J.4. That's our neutral current. In order to balance these vectors or these force lines, we need to have a current flowing in the neutral wire of, down here, IN equals 10 minus J 0.4. That is a solution to a three-phase unbalanced star system with an ideal neutral that we've solved for currents. In my next tutorial, I'll go through and I'll use these same values. We'll go through and we'll solve for power. We'll see how much power is dissipated in each of these loads, what is the real, the reactive, and the apparent power in each of these loads. And that'll be in the next tutorial. Recapping what we've done here is we took our single-phase system and we created it in a three-phase system with our other two phases each 120 degrees apart. This is the standard sort of schematic that we'd use, and here it is presented in the time domain. The voltages. We've put it through an unbalanced load, which is a realistic load. Okay, very rarely will you ever encounter a perfectly balanced system because they simply don't exist. They're like unicorns. Here we are here, our unbalanced load, and we've gone through and we've calculated all of our currents, phase A, phase B, phase C, and our neutral current here. IN is 10 minus J 0.4. We've presented all three of our voltages and all four of our currents here in our neutral, in our phasor diagram, and I showed here our neutral currents, our phasor currents in the time domain to show you that they don't all add up to zero. That's why we have a neutral current. Thanks for watching.